Well, welcome to lesson 6 in our chapter on complex numbers. We are going to learn about complex numbers. I believe this is review for you, but just in case, we'll make sure to explain things very completely for you so that you can be successful in this section. And your learning targets for this section are to understand what a complex number is, how that relates to our real number system that you're used to dealing with. You're going to be working with complex numbers, adding, subtracting, multiplying, and dividing them. You will also use complex conjugates to help you be able to manipulate different algebraic expressions. You will use the discriminant to identify the type of solutions of a quadratic equation. And you're also going to solve quadratic equations with complex number solutions. So we're going to start off by defining what a complex number is. A complex number is defined by this italicized letter I, and it stands for the square root of -1. So whenever we have a square root of a -1, we call that I, and it is a complex number. Now, a complex number has two parts. It has a real part and an imaginary part. And we write it as a plus bi, where a is the real part and bi is the complex or imaginary part. Now, we get complex numbers or imaginary solutions when we have things like quadratic equations like you'll see over here, where we have x squared plus 1, where it never touches the x-axis, so we don't have any zeros. There's no real solutions. And when that happens, we get complex solutions. Okay, we get solutions where we get a square root of a negative. So we're going to be working with these complex numbers and finding solutions that are in complex form. So first off, it says write the following radicals as complex numbers. So what we want to do is simplify this so it has a real and an imaginary part. And so the square root of -25 could be written as the square root of 25 times the square root of -1. We can break those up. Well, you recognize the square root of 25 is 5 and the square root of -1 is I. So this is just written as 5i. I mean, you don't need to put the 0 plus 5i. The 0 is there, but we don't have to write that when it's a 0. Square root of -60 we could write as the square root of -1 times the square root of 60, and then we want to simplify the square root of 60, and 60 breaks down into 4 and 15. 4 is the largest perfect square contained in 60, so that will come out. The square root of 4 is actually a 2, and the 15 is stuck because that's a 3 and a 5 and there's nothing that will come out. So we get 2 times I is that -1, the 2 comes from the 4, and then the 15 is still under the radical, so 2i square roots of 15. Letter C, we need to simplify. 5 squared is 25, and when we multiply these three negative numbers together, we get a -72. 25 minus 72 under the radical is -47, so this simplifies as the square root of, I square roots of 47. To add or subtract our complex numbers, we're just going to add the real parts and add the complex or imaginary parts. So in this example, the real parts are 7 and 6. They add to 13. The imaginary parts are -3i and -1i, which give us a -4i. To multiply complex numbers, we're going to use FOIL. Remember, that was first, outer, inner, last, which is what we use whenever we're multiplying two binomials together. So in this example, we have 7 minus 3i times 6 minus I. Our first terms are 7 and 6, which will give us 42. Our outer terms right here are 7 times -1i, which is a -7i. Our inner terms are -3i times 6, which is -18i. And our last terms are -3i times -I, which is a +3i squared. Well, now we can simplify this 3i squared thing, and we can simplify the -7i and -18i. The 42 stays here. These two combine to give me -25i. And I squared is the same as the square root of -1 times the square root of -1, which is just -1. The radical drops out. So this is really a -3. And 42 minus 3 gives us 39, and then we have -25i. Remember, it's the real part first, then the imaginary part. So here's a good reminder for us. Graphing calculators can perform many complex number operations for us. We should be able to do those with or without the calculator, so make sure you understand how to do that. I'm going to fill in a couple of things, raising a complex number to a power. So I is defined as the square root of -1. If we square that, we just get -1. Well, if we cube it, we get -I. And if we take it to the fourth power, that's just like taking I squared squared. So it's like -1 times -1, which is +1. And anything you repeat down here, I to the fifth, this will just repeat. I to the fifth will be the same as the square root of -1. This will be I to the sixth, seventh, eighth, 9, 10, 11. It'll just keep repeating in that same pattern. So what if we have 2 minus I, the quantity, to the third power? Well, that means 2 minus I times itself 3 times. Well, what if we just take two of these at a time and expand it? We get 4 minus 4I plus I squared, and we can simplify that to 3 minus 4I. Remember, the I squared is -1, so we have 4 minus 1 giving us the 3, and the minus 4I is still there. Bring down this 2 minus I. This is the third factor of 2 minus I, and now we're going to FOIL this again. So our first terms will give us 6. Our outer terms gives us minus 3I. Our inner is minus 8I. And our last terms are plus 4I squared. Well, remember this I squared is just a -1, so -1 times 4 is -4, and 6 minus 4 is 2, and 2, well, when we combine the minus 3i and the minus 8i, we get minus 11i. So that is our final solution. I also wanted to show this to you on the calculator so that you know how to do this. Down here, this is the second function of your decimal point here. So if we just took our original equation, take a parenthesis and go 2 minus, and then we're going to go second period to get that I in there, and a parenthesis, and then raise that to the third power and hit enter. That gives us our solution right away on the calculator. So we get 2 minus 11I. So it's a good way to check your work. All right, complex conjugates. We're going to use complex conjugates to help us simplify algebraic expressions, especially when we have complex numbers in a denominator. So the complex conjugate of a number is just the real part, but then changing the sign of the imaginary part. So if we have a complex number that's a plus bi, the conjugate is a minus bi. Okay? So let's take a look at how to find the conjugate. If we have 3 plus 2i, what would the complex conjugate be? Well, it's just changing the sign of the imaginary part. So this one's going to be 3 minus 2i. Likewise, we have -5 minus 4i. This would be -5 plus 4i. You only change the sign of the imaginary part. Same thing for part C. Our conjugate will be -1/2 minus the square root of 3 over 2 times I. Well, now let's use the conjugate to help us find the quotient here. If we're dividing things, one of the rules in algebra is you cannot have complex numbers in your denominator. So we need to get rid of those so that we have real numbers in the denominator. So we're going to have to multiply the top and the bottom by the complex conjugate. So this fraction right here that I'm multiplying is the same as 1. So essentially I'm multiplying by 1. Well, if I distribute in the numerator, I get 8, or I'm not going to distribute, I'm going to just leave it there. 4 times the quantity, 2 plus I. And then multiplying using FOIL in the denominator, the first terms I get 4. Now my inner and outer will always drop out. I'll get a plus 2i and a minus 2i. That is by design. If you've done your complex conjugate correctly, the inner and outer terms of FOIL will always drop. And then my last term is minus I squared. Well, minus I squared, that's just I squared is -1. So this is 4 minus a minus 1, which is 4 plus 1, which is 5. So this now is our solution. Notice we have a real number in the denominator. So multiplying by the conjugate gives us a real number in the denominator. Over in example B, we're going to multiply top and bottom by the 5 plus I. And go ahead and, you know what, this would be a good time for you to pause the video, try to work on B and C on your own, and I'll show you the answers quickly when you come back. All right, I hope you had a chance to do that. Here is what you should have come up with. Multiplying the numerator using FOIL, you get this. And in the denominator, we have 25 minus I squared, but then we can combine some like terms and simplify in the numerator. Our I squared here is the same as -1. 15 minus 1 is 14. 25 minus a minus 1 is 25 plus 1. But we have a factor of 2 that's common in the numerator, so let's factor that out. When we do that, we have 7 plus 4i is what's left. And then the 2 and the 26 can cancel. So we'll just have 7 plus 4i in the numerator and 13 in the denominator. This is our final answer down here. Over here on the right-hand side, complex conjugate 7 minus 2i. Multiplying using FOIL, we get that. Simplifying our terms, our final answer is negative 20 minus 17i all over 53. All right, the quadratic formula, the part of that under the radical, the b squared minus 4ac thing, that is called the discriminant, and that tells us the kind of solutions we have. And if that number is bigger than 0, if we get a positive number under the radical, then we have two real solutions. If it's exactly equal to 0, then there's one solution and it's repeated. So you might get something like 1 and 1. If it's less than 0, meaning you get a negative number under that radical, then you have complex conjugate pair solutions. You have two complex or two imaginary solutions. So that discriminant helps us identify what kind of solutions we have. So let's do a quick example. Here's a quadratic equation. A is what's in front of x squared, b is 2, c is 5. You know how to identify those. And we only have to plug it into the discriminant here. We don't have to do the whole quadratic formula. So b squared minus 4ac, b is 2, 4, a is 1, c is 5. So we have 4 minus 20, which gives us a negative 16. Since this is negative, we have two complex solutions. That's all for this video. We'll see you next time.